Hi, welcome back, everyone. We are very happy to have Daniel Reichman here, and he's going to tell us about LLMs to do NP-complete reductions.
Okay, hi everyone. Very nice to be here. And thank you very much, Adam, for the invitation. And I'm going to talk about using large language models to prove NP-completeness. And this is joint work with a bunch of folks from WPI. The first two are PhD students, second two are undergrads, and Neil Heffernan is a professor at WPI, expert on online education. So what am I going to do here? So I should say that I'm a newcomer for AI in math. And I'm generally a great believer. Many people, I think, are a great believer. There's a lot of news about this. We see blog posts all the time. Pretty certain that AI carries a very big potential for math. So it is promising. I should say that maybe in contrast to the impression that you get from some of the blog posts or Twitter or whatever, AI for math and AI in science, and more generally, I have some work in this domain. It's challenging. It's hard to make work. And I want to talk a little bit. One thing that I will discuss is the kind of challenges that you encounter. Some of them are specific to math. It turns out there are all kinds of things that we as a mathematician do, and we think they're very obvious and easy, and we don't even think about it. But then when you have to use AI and machine learning, it's a very, very different story. So I'll talk a little bit about these as well. So NP-completeness, I'm not going to get into the entire definitions of NP-completeness, but just some background. So the idea behind the NP problems is that these are problems that are easy to verify, that you can verify them in polynomial time. And when you're talking about the NP-complete problems, the common belief is that they're hard to find. One classical example that we have here is that of a Hamiltonian cycle, a cycle that passes exactly once through the nodes of the graph. So if you need to verify that a given cycle is Hamiltonian, that's very easy to do. You have an efficient algorithm that does that. On the other hand, finding a Hamiltonian cycle or proving that a graph has or doesn't have an Hamiltonian cycle is very challenging. I think you have some graphs where to this day we don't know if they have Hamiltonian cycles or not, and from some others it has been a challenge. So this is a classic example of a problem in NP, and it's also NP-complete. I'll get into the definition of NP-completeness shortly, but I should just say that in the 70s, Cook and Levin proved independently that the satisfiability problem is NP-complete. And in the beginning, I think it was around 72 or maybe earlier, it seemed like an isolated phenomena. And then Richard Karp from the University of California, Berkeley came and illustrated that you have a lot of NP-complete problems, that it's far from an isolated phenomena. And afterwards, we've seen an explosion. And so you have this very nice book by Michael Gary and David Johnson, and this books, which is very relevant to this day. I think it was published in 78, lists, I don't want to say thousands, but probably hundreds, if not dozens, of NP-complete problems. And ever since this book, we have seen many more NP-complete problems, and NP-completeness is occupying a central place in engineering, in physics, in biology, economics, and also in mathematics. So Christos Papadimitriou talked about the contribution of NP-completeness. And very, do we have a question on Zoom or something? Or people are joining? Okay.
People are joining.
Okay. I'm not monitoring the chat or anything. So if people in Zoom have questions, just let me know. So what is a central thing with the idea of NP-completeness? The idea is a polynomial time reduction. So we have two problems, X and Y, two decision problems. One example for a decision problem, just deciding if a graph has an Hamiltonian cycle or not. And then we have a reduction. So roughly speaking, a reduction is just a mapping from one decision problem to the other, such that if x is a yes instance of capital X, then f of x is a yes instance of capital Y, and so on. We expect the reduction. One thing that is very, very important is that the reduction will run in a polynomial time. Otherwise, with these kinds of problems, you can just have exhaustive search and find trivial reductions. So here's just one example, one of the textbooks examples for reduction for the satisfiability problem. So what is the satisfiability problem? You're giving a conjunctive normal form. You just get a conjunctions of ORs, and you want to know whether this formula is satisfiable or not. So this is maybe the first NP-complete, sort of the first, if not second, NP-complete problem. And we have satisfiability. We want to know whether the CNN formula is satisfiable or not. What does it mean that it's satisfiable? It has an assignment for the variables such that every clause evaluates to 1. And 3-sat is the same with the additional constraint that every clause has exactly 3 literals. So it turns out that 3-sat is also a difficult problem, also in NP-complete. And suppose that we know somehow that satisfiability is hard. We don't believe that there is a polynomial time algorithm. So what I want to claim is that you have that implies that the independent set problem is hard as well, is likely to be intractable as well. Why? Because there is an efficient reduction from the independent set problem to the satisfiability problem. What is the independent set problem? You're given an undirected graph, and you just want to know whether it has a subset of vertices of cardinality exactly k, or at least k that doesn't span any vertices. So what is the reduction? The reduction, essentially what it does, it just puts a triangle for every clause, and it just connects any 2 literals that are have a different plurality for one another. And then, yeah, what you do is you just take every literal and connect it to each one of its negation, each one of its negation. So this is the reduction. It's not very hard to see that this reduction can be done in polynomial time. I'll get, by the way, to this. It's not very hard to see a thing later. And then one thing to observe is that the formula, the SAT formula, is going to be satisfiable if and only if you have an independent set of size exactly k. What is k? K is just the number of clauses. And the point is you're just going to take a clause that a literal, sorry, that evaluates to 1 from every clause. And then just by the way you put the edges between the triangles, you get that this thing has to be an independent set because things are consistent with one another. So because of that, you don't get any edges. So because of that, we have just shown a reduction from a 3 satisfiability to independent set. And that means that if we believe that 3 satisfiability is hard, it doesn't admit efficient polynomial time algorithm, so it does the independent set problem. So what is the connection between NP-completeness and pure mathematics? So NP-completeness is a concept that arose from theoretical computer science, but it turns out that NP-completeness has a lot of connections to mathematics, to combinatorics, but not only to combinatorics. It has connections to topology. So here we have some people, some experts from topology studying all kinds of knot invariants and proving that computing them exactly is NP-complete. This paper contains quite some intricate topological and geometrical arguments. And we also have other examples that show NP, essentially show NP hardness. And we have a recent paper by Mintzer and Safra and Hot talking about the 2-to-1 conjecture. And we also have a paper by Iri Dinur and Muli Safra talking about the hardness of approximating vertex cover. I don't want to go into the details of these papers. These papers are very, very complicated. One thing I want to say about this paper by Dinur and Safra is that it uses some very sophisticated combinatorics to prove NP-completeness, some set intersection theorems. And it's actually an interesting question how we can use AI to find these connections. One of the challenges in proving something is NP-complete is finding connections between mathematical domains that might not seem related to what we're trying to do. So what is the recipe to prove that the problem is NP-complete? What we want to do is we want to prove that the decision problem belongs to NP. That just means that it can be verified efficiently. Given a yes instance, we have an efficient algorithm that certifies that. And just think about the Hamiltonian cycle example. And then what we want to do is we want to show that an NP-complete problem Y efficiently reduces to X. So just find the kind of a reduction that we gave before. So how do reductions relate to machine learning and large language models? So here we're going to mostly focus about large language models, although I should say that there is plenty of room, I think, for other users of machine learning, maybe some of the stuff that Adam has been doing, I'll get to that later. So when you talk about using large language models or machine learning more generally for math, one of the things that you're tempted to do is to build data sets. You want to build data sets. So building data sets, from my experience, and not only from my experience, is challenging for math. So everybody who taught math classes knows that it's hard to construct dozens and dozens of examples, of solved examples. So this is something that is actually hard. And when we're talking, for example, about probability, even combinatorics, all kinds of mathematical things to generate like a big data set of interesting problems, this is something that is far from driven. And I think for many mathematical domains, it's actually unresolved. I haven't seen big data sets that relate to such domains, such as, for example, probability. When we're talking about reductions, it's easier. It's easier. Why is it easier? Because you have, so for two reasons. One reason is that you just have thousands of reductions out there, and then many of these reductions are not too complicated. When you build such a data set, if you're going to start putting in it very hard problems, it's not going to work very well. It's just going to be too hard for the machine learning model, and it's going to be very hard to verify. With reductions, just as the example you have seen, this is an easy example, even if my presentation of it wasn't ideal. It gives you a good idea of a problem that on the one hand, it's not completely trivial. It's easy, but not completely trivial. And on the other hand, it can be verified, and you have lots of these problems. So this is something that is also good. One thing I also want to emphasize is that when you talk about the data set of proofs of reductions, there is an emphasis of the story, of the explanation. So I should say that this is different than other data sets I'm aware of, that you look more on manipulations, numerical manipulations, symbolic manipulations. For example, there was a very nice talk here at CMSA by Stanislas Polo. I think it was, I don't know, a year or two ago, very nice talk. So the kind of data sets, if I recall correctly, I might not be recalling correctly, he was talking more about data sets that have like all kinds of symbolical and numerical manipulations. Our data sets is a little bit different than that. I'll talk more about the data set soon. So you have all kinds of questions. One question is like, how well do large language models do on proving NP-completeness by constructing reductions? And another question is like, when we build a data set of reduction, is this thing going to help us? So this is a project in progress. We have some partial answers, but definitely not answers to all of them. Yeah, this is So this is something that we spoke about. I just want to say one thing with respect to these reductions. Many proofs of reductions are error prone. You have a lot of errors out there. It would be very nice if large language models will be able to detect such errors. You have lots of errors. Why do you have lots of errors? One speculation is that you have lots of, it's easy to see and so on. Then it's easy to see, but it can lead to a lot of errors. So you have quite a few errors in reduction. This is something that is explicitly mentioned, by the way, in papers dealing with reductions. What is the Karp dataset? The Karp dataset, it's named after Richard Karp from UC Berkeley, who was one of the people who contributed a lot of the study for NP-completeness, proved that many problem combinatorial optimization are NP-complete. So the Karp dataset has 90 reductions for NP-complete problems. So when you construct a dataset, one question that you have is how do you choose the problems in your dataset? So I don't have a very good answer. It's a little bit heuristic. We chose some famous problems that are cited a lot. We chose some things from academic papers. It was a little bit of a heuristic choice. We looked also at proofs that are relatively elegant, not more than, let's say, 2 to 3 paragraphs. not very long. Some NP-complete reduction can be very long and tedious. One thing that I want to talk about is about the format of the proof. The proof is written in human language. One thing we took great care is to prove everything, because with these reductions, you have a lot of compressions. We didn't want any kind of a compression for a large language model. We proved everything. We proved everything with respect to the correctness of the reduction. We didn't get into the polynomial time to proving that the reductions actually take polynomial time. That would be actually pretty tedious and would lengthen things considerably. For the future, it would be very interesting to also add the proofs that problems are in NP. And we also did add this in our data set, and to prove that the running time of reductions takes a polynomial time. Usually when you look at proofs that you have at textbooks and papers that just say it's easy to see or give a line or two and don't give the entire whole detail. So we didn't want to get into that, at least at the first step. I should also say that the size of this data set is relatively small. Many data sets have thousands of problems. We'll get to that later. So now what we wanted to do is we wanted to evaluate how things perform on the CAP dataset. So the first attempt that we did was to just pick more or less at random eight reductions out of our dataset, and then just see how things work on that. So the first thing we checked is the Llama language model, the Llama LLM, and we just checked how well it does. I should say something with respect to the grading. So the grading was 0, just means that it's complete nonsense. The reduction doesn't make sense at all. 1 means that it has some flaws, but it does have some truth in it as well. It's not a complete failure. 2 means that you might have minor errors, or it might be perfect. So it's sometimes there are some minor errors, so we gave it a 2. And then, when we started this, Strawberry actually didn't exist. And when we looked at the performance of a language model like Llama, it doesn't do very well. The average is 0.875. And when we fine-tune on this data set, when we fine-tune on the CARP data set and look at the Llama reduced the fine-tuned version, it does actually better. It does actually better. So we were pretty happy with this thing, because one thing that we could say is that reductions is a challenging task for large language models. And then Strawberry came, and then the question was, so for those of you who don't know, Strawberry is a new model from ChatGPT that was trained to do better in reasoning and mathematical problems. Strawberry actually does pretty well. There was this one problem that it produced errors, but with the other things, it did very well. And then the question that we had in mind was, well, does Strawberry, solve any NP-complete problem? What's going on here? How do we evaluate Strawberry? So to assess this, what we did was we just chose a new set of NP-complete problems that did not belong to our data set, and want to know how well does Strawberry does on that. Now what we did was we still chose questions that had relatively short solutions, but we chose things that are known to be more challenging, just harder. The reductions are trickier to find. So for example, we chose one reduction that people claimed for a problem that it was NP hard, and actually afterwards it was found that the proof was wrong, and some people corrected it and had like 1,200 citations for the correction. So this is one example for a challenging problem. Here you have a list of the problems, and what we see is that Strawberry now does worse, and Llama also does worse. And the interesting thing is that here fine-tuning helps you less. It still helps, but the effect of it is less pronounced. It just means that once you jump into mathematical difficulty, you can't expect just fine-tuning on the dataset to solve your problems. You probably need another component. One thing that we looked into was also how well does fine-tuning on existing datasets such as math and MGSN, how well does fine-tuning on our dataset helps? And it turns out it doesn't help a lot, and maybe because the dataset is small. Yeah.
How do you pose the problems? Do you give like the definitions from?
Yes, that's a very good question. So we give the complete definitions of the problems, and then we ask to prove that they're NP-complete. That's a great question. So we just say 3 coloring is so and so. Click is so and so. What is balanced bipartite click? Just a complete bipartite graph. So we give the complete definition. The data set, I should say, is pretty long.
Like scrambling or just putting like nonsense words instead of names, just to check. It's taking up on things like this. So we didn't try that. And of course, with these results, it's made necessary, like diversity 2, 2, 2. And then you start.
Yeah, one thing I should say about the data set is that even like with the 90 things that we have, like we're talking about more than 100 pages, maybe more than 150 pages, that it's pretty massive.
Because again, a lot of this stuff is clearly in the training.
Yeah. Yeah, I agree. It might exist already in the training setting. So some takeaways. So reductions are challenging for most LLMs. Another takeaway that is important, and I kind of glossed over, and again, this is something that as mathematicians we kind of know, but we at least I didn't think about it enough before this. So when you talk about mathematics, it's not only about finding the proofs. It's not only about finding the proofs. It's also about evaluating the thing. So in your data set, you need to find a way to evaluate the answers. You need to evaluate all these, the answers of all these large language models. That is labor intensive. You can ask my grad student, it's a lot of work. One thing that would be great is to find a way to automate that. I'm sure people have looked into that, by the way, but I'm not aware of good solutions. Of course, you have Lean, but if you want to transfer things from natural language to Lean, this can be doable, but it's pretty labor intensive. So one question is whether we'll have if we have a larger data set, we'll see actually improved results for fine-tuning. We're planning to get a larger data set. Another question is like, what is the cognitive primitive that the large languages model is learning or acquiring when it looks at all these reductions, maybe analogical reasoning. So this is something actually interesting to look into, that we plan to do it as well. So one question is like, do we expect large language models or machine learning to produce new reductions, things we haven't seen before, or maybe resolve or open questions? So I want to risk and say that this is something that I think we will see relatively soon. I don't want to say exactly what I mean relatively soon, but in a matter of years, I think we will definitely see that. One thing that you see when you give these examples is that large language models seem to be missing, maybe Strawberry to a lesser extent, is critical thinking, is trying to prove yourself wrong, trying to search for counter examples. This is very important for reductions. You find these reductions and you want to know whether they're right or wrong. So the first thing that I do and many others is to try and look for counter examples. I don't know if large language models do that, but I think that some of the stuff that Adam and others have been doing to try and find counter examples might be useful here. And when you talk about reductions, oftentimes you have very complicated gadgets, all kinds of combinatorial constructions that transfer you from one instance to the other. So then I think it's a very interesting question to be able to discover gadgets using machine learning, using reinforcement learning. Here we have just one example for Berman and Karpinski, 1999. So for example, when you want to prove that certain problems are NP-complete on bounded degree graphs, for example, the independent set problem on bounded degree graphs, more precisely when you want to show that they're hard to approximate, you need very complicated gadgets. You need so when I say very complicated, it can be dozens of vertices. I think it will be very interesting to use machine learning or reinforcement learning to find better gadgets than these or unknown gadgets. And with this, I'll end. Thank you very much.
The project could be considered a benchmark.
Right, so it is indeed, so then that's very true. The main thing is a benchmark, and we are definitely going to share it. I should say that sharing it is a little bit challenging because, you know, many people teach these things. So we don't want to just share it in the open and then, you know, it will be impossible to share it. So what we'll do is people will contact us and then we'll share it. But yeah, I think the major contribution here is the data set, absolutely, in the benchmark.
And also, if you hold it, then you can maybe avoid future language models training.
Yeah, exactly. That's not a data set that it's not like the math data set that you can just release in the wild. You have to, we plan to keep it. Yeah.
So I really liked your point about the discovering gadgets, because that's something I've been thinking about. And I think in a lot of parts of the mathematical workflow, we've seen machine learning make some strides, bigger or smaller, depending on what it is. but that's somewhere I haven't seen too many examples. You know, for really hard problems, you have mathematicians coming up with whole new fields to kind of like work their way around to a solution. Have you seen any evidence of this, even small examples?
That's a fantastic question. So first of all, I strongly agree with what you say. I should say that there is a paper by Professor Madhusudan, who is not too far from here, and other well-known like David Williamson, Luca Trevisan, and Gregory Sorkin. They have a paper about finding reductions automatically with linear programming. That's a paper for more than 20 years ago. It's a very nice paper. It also has some nice theory in it. It didn't, I think, translate to people actually using this software when they try to look for reduction. So I think that's an open domain.
Well, how would you formalize this problem of finding the edges if they like the problem?
Yeah, that's a great question. I think it depends on the problem. It depends on the problem.
So that's a big class of gadgets.
So I think that between constraint satisfaction problems, for example, you could say, like, can you find a transport? Like, so I think what you would want to do is just replace. So for constraint satisfaction problems, which is, by the way, the Sudan paper I mentioned, they want to take like a clause that is like, I don't know, 3 sat, and then translate it to equivalent clauses that have a different CSP form, like linear equations or something like that. And then you want to find the minimum number of linear equations that you can place a 3 sat clause, so something like that, which is pretty tedious, by the way.
Once that's done, so
In your prompts, you said you just give the 2 definitions of 2 problems. Have you tried to also give like some examples from your data set? So this is what the reduction looks like. Can you do this for these 2 problems?
No, we didn't do that. That's an interesting
point. Do you think that might help, or do you think that that's going to make a difference?
I don't know. Yeah, you have to.
So here you zoomed in on this kind of class of problems because there's lots of examples. You have to come up with a story, and it seems like a really good fit. Can you think of some other class of problems that are other parts of mathematics which would also be similar, where there's lots of examples, be a good fit for problems?
Yeah. So that's a great question, and I think that maybe the closest thing that comes to mind is this book of Lovash with the combinatorics. So yeah, the thick book with because it has solutions. I think everything is solved there, right? You probably know this book much better than I, but Lovash has a very nice book with solved questions. So I think that most of the solutions there are also not too long, because again, like, you don't want to start giving things where the solution is like, I don't know, like more than 5 pages long. I think it's.
You mean the book on graphons, or do you mean the proof?
No, not the book on graphons. There's combinatorial questions and exercises. So I think this is.
Those are some really hard ones.
Yeah, so I think you would want to choose like the easier ones. Yeah, I think what you could do, like maybe again with combinatorics, is that, and this is something that you can also do here, is use some kind of data augmentation. So for example, with reductions, it's very easy to use some kind of data augmentations. We didn't do it a lot. What do I mean? I just mean you prove that 3 sat is NP hard, and then it's you can also prove that 4 sat is NP hard, and do all kinds of examples like that. So I think with combinatorics, maybe you could somehow think about somehow augmenting examples and somehow increasing your data set. I don't know. So for other domains in math, I think it's challenging. I mean, many of the domains in math, like for example, probability, like you have like this set of questions. Once you want to add more questions that are not too hard, have a nice elegant solutions, at least for me, this is something that is hard. Maybe the same is true for linear algebra. I'm not sure. I haven't taught linear algebra for a long time.
Okay, I will just move these out of the way and hopefully
That's perfect.
folks can see.
Yeah, good enough. Okay, excellent. Our next speaker is Henry Koenig, and he's going to tell us about a cool new data set that they've developed for algebraic combinatorics.
All right, well, thank you to the organizers for a wonderful week, and for the other parts of the program that I wasn't able to attend in person. So today I'll be talking about a collection of data sets that we've been cobbling together. So this will be mostly about lessons learned in trying to do that. Some of the things we've gathered in this, emerging field of AI for math. Okay, so this is a collaboration. Actually, this is an outdated slide, but largely a collaboration between Pacific Northwest National Lab and the machine learning researchers there, and currently mathematicians at University of Washington. We're hoping to grow that, so if this is something you're interested in, we welcome participation. I think ultimately this should be something that's not two groups, but much larger if it's going to be successful. And it's certainly more work than we can handle on our own. So I don't need to tell this group that machine learning for math is an emerging field with a lot of promise and opportunities. I think it's striking that it has been applied across many domains of mathematics. This is not something that's concentrated in one place. This week we've been talking about combinatorics, but of course there's interesting work being done in algebra and geometry and PDEs and number theory, things like that, knots. And I do want to highlight that most of this work was actually inspired by this work that Jordy was a part of with DeepMind, where they made some progress on problems in knot theory and algebraic combinatorics or representation theory, which I thought this was really cool and something that could be applied much more broadly. Okay, so in thinking about AI for math, one way you could break this down is sort of in terms of the mathematician's workflow. So this is a diagram that I'll admit I did not put a ton of thought into, but I sat down the night before I was supposed to give a presentation about this stuff and tried to think through what is one representation of what the process that a mathematician might go through when they're doing research. And just based on introspection, mostly from back when I was proving things as a PhD student and postdoc, I think one way that you could represent this is sort of a cycle between maybe you talking to someone, you're reading papers or something like that, and you come up with a question, and you might initially have very little intuition about what the answer to that might be, or what even the right question to ask is, and so maybe you'll go and you'll do a bunch of examples. Or look at a bunch of data or something like that, play around with pencil and paper, try to develop some intuition. Maybe then it makes sense to go back and review the literature. Now that you understand things a bit better, go back and talk to people, ask questions. And at some stage you might sit down and try to actually prove something. And I think more than likely, this cycle will continue several times before you actually reach some final point. So in when my first paper, I was given a problem at a conference by an experienced mathematician. I went and I computed a bunch of things with silly little diagrams. I went back to literature, realized the thing that I was computing was actually known in a different form, and proved some pretty simple theorem. So this work is largely concentrated on this side of the house, on the sort of raw mathematical data. There's also a lot of interesting work being done on the proof side, which we've heard about a little bit this week. And I think there's also a lot of opportunities in literature search and review, and how do you enable different fields to interact with one another, even if they might have different jargon. Okay. And I did want to tie this to some other interesting things that are happening in machine learning more broadly. So I think there's some interesting connections to an emerging field called neural algorithmic reasoning, which I don't know much about beyond being a bystander, but seems to have some important connections where folks are looking at incorporating machine learning into classical algorithms and things like that. And there's a lot of interesting reasons you might want to do that, even if we have good algorithms for some problem. Okay, so this again has been well teed up over the week, but common data sets are an important thing in machine learning, and they've been a big driver of progress. When everyone's working on their own data set and developing their own methods around it, it can be really hard to compare methods, or even to kind of speak in the same language. Now, arguably, in some fields of machine learning, this has gone maybe too far, where a lot of the work is now driven by like very tiny incremental improvements on some very canonical data set that may not represent the actual problems in the real world anymore. But one thing we recognized as we started thinking about AI for math was that there's a lot of really cool work being done, but it's either being done on by the machine learning community on problems that are like toy problems, like multiplication of small finite groups or things like that. There's good reason for why they're doing it there, but it doesn't really represent research mathematics that well. Or it's being done more mathematically motivated, but there's a high barrier to entry. So it's done work done for experts within their field, written for those experts, and it could be really hard for someone who, say, was interested in AI for math, but was not an algebraic geometer or whatever the particular field had to be to get involved with. So we thought it would be great to sort of collect a place where you could have open problems or problems that represent work that is like foundational to a space in one place that's sort of set up so that someone could just pull them down and apply machine learning to them. And so we created this repository for ML datasets on algebraic combinatorics, or we are in the process of creating it. If you go and look at the website, it's still a bit of a mess. But the goal is to include open problems and classic problems for which new approaches would be interesting. So an example of a classic problem might be calculating characters of irreducible representations of the symmetric group or something. So this is a very basic thing. It's at least 100 years old now, or it's close to that. But it's a foundational result, and if you could find a different way to do it using machine learning, that would be interesting. And it'd also just be interesting if machine learning could rediscover known ways from more of an ML perspective. I should say, so we've gone back and forth on whether this, initially we were calling this a benchmark. I actually don't think it is, because I don't think the goal in this case is to just get high accuracy on these problems, although that may be interesting. It's more to try to set things up for scientific discovery. And more than likely, at the end of the day, you'll need an expert to kind of help you work through it, but you can get a start to it. I was inspired a lot by recently, I think it was NeurIPS last year, looking at some of the mechanistic interpretability work, where they were really doing like very detailed exploration of how models were doing computation for problems, and trying to reverse engineer an algorithm out of a model. Now, that's much harder when you don't know the algorithm beforehand, but also the stakes are much higher. So if you could use some of these sophisticated interpretability techniques, or more likely a collection of them, and all throw them at this a performant model and extract a part of a solution or an insight that could lead to a solution, that would be I think a big win. And this has already been done to some extent in certain cases. I probably don't have to tell this audience what algebraic combinatorics is. It's the combinatorics week. What I will say is that there's a few reasons for why we chose this. So we wanted a field that had deep connections to other areas of mathematics. So you can imagine a result in algebraic combinatorics, being able to tell you something about some sophisticated geometry or representation theory or something like that. Also, though, the problems, at least on the face of it, are easily explainable in many cases. So you could explain to a high school student the surface level, at least, of what needs to be done, even if the broader connections require a lot more background. Being discrete, I think this was written in the abstract for this week, but being discrete, these things are often more easily represented on a computer than, say, like a manifold or something. And also, there's a lot of good software out there already for generating these things. So we had to do very little actual math computation for generating these data sets. It was more just like figuring out some problems and then calling the appropriate Sage code, for instance. So some of the data sets are represented here. So we have some problems about lattice posets on lattice paths. We have a cluster algebra quivers problem. It's a little simpler than the one that has been posed in this workshop. But we already have some initial results for it, which was cool. Some known problems like RSK and symmetric group characters. Some things about symmetric polynomials like KL polynomials and Schubert structure constants for Schubert polynomials. And a few other things as well.
Can you read some of those out for us, because they're too small?
Oh, yes, sure. So in this top one, and I'll talk in a little more detail about these in a few of these in a moment. So there was an open question about comparing two partial orders on lattice paths, which I'll say more about in a second. Weaving patterns have to do with representations of the longest word, and the problem involves trying to come up with a characterization in terms of this matrix form. The cluster algebras quivers question is about being able to distinguish between mutation equivalence classes for finite type and affine type. Some of those are known, some of them are not. I talked about symmetric group characters, KL polynomials. This at the moment is just predicting coefficients, but probably a more specific problem needs to be formulated. RSK is just seeing if you can train a model to learn the Robinson-Shedstead-Knut algorithm, which of course is a fundamental thing in algebraic combinatorics. There's a problem, this Grassmannian cluster algebras problem actually comes from the clustering cluster algebras problem for the paper, for those who know it. So we're interested in bringing in outside data sets as well. Schubert structure constants just looks at given two Schubert polynomials, can you predict the structure constants, which a combinatorial interpretation of those is an open problem. And then this M height function, which is partially blocked by the participants, is just an intermediate result in a recent proof of an open conjecture that my collaborator Sarah Billy suggested would be interesting, since it was one of those things that you had to invent to solve a different problem. It turns out to be pretty easy for the models to solve. So for some examples of this, so this problem, so one can look at partial orders on lattice paths that are on the travel from 0, 0 to n-1 and never cross above the diagonal, this diagonal on this grid. And only travel east and north. And it turns out these are important for some things I'm not qualified to talk about, but some cluster algebra results, Markov numbers, Lagrange spectrum uniqueness conjecture. And these were posed by Ralph Schiffler in a recent paper. And at the process, he defined two partial orders on these that come from some of these connections. They relate to continued fractions. I don't remember off the top of my head the exact definitions of them. And he posed this problem to study these posets. So you can go ahead and start to make a data set with these. They're easy enough to compute. You can compute lots of them, probably more than you can train on. And of course, one of the nice things I think from a machine learning perspective, for someone who comes from sort of the more mainstream machine learning, is that whereas in most of my work I have to be very careful about data and I have to use, it's scarce and I have to use every bit of it. In this case, I can generate as much as I want by scaling up the grid size. So when we're on a 13 by 12 grid, there's already 700,000 lattice paths, or lattice path cover pairs, which is a lot. So the way that we formulated this was to so study these partial orders. That's not very specific. How do you start to translate that into a machine learning problem? Well, there's a lot of ways you could do it. We tried something fairly naive by looking at turning it into a classification problem. And what we ended up landing on is collecting sets of covering pairs, where the cover of covering pair AB, where A covers B or B covers A, is either holds in one partial order or the other and not both. So you can ask why choose that, and I'll say in a second some comments on that, but it's certainly not the right way. There's probably more ways to do it. But translating things to a simple machine learning format like binary classification is nice when you can. So the models do really well at this. So even logistic regression gets 75%. So this is balanced to be about 50-50 each class. So 50% is guessing. A small transformer can get 99.5%. So it's learning something. So it may not be learning anything interesting. It could be, and this is, I'll talk about this in a second, it could be that the model learns like some very obvious clues that are not interesting mathematically, but cover like a wide spectrum of examples. So you have to be careful. But on the face of it, it seems like the model's learned something, and we're just starting to analyze this. So I unfortunately can't say too much more than that. So there's an art to trying to convert these to a sometimes not super specifically worded conjecture or question into an ML problem. We found this the best thing to do is try to do the naive approach first and see if that works. One thing we noticed, so I think when we first started out, we said was, okay, we want to compare these partial orders, so let's just try to be able to predict whether two lattice paths are either greater or less than or incomparable, and which partial order that's true in, or something like that. And what we found was that the model did excellent and it seemed to learn nothing useful. So most examples are predictable for reasons that are not interesting at all, and they don't really get at the core of what is it that we want to learn about these things. So this is something we've seen over and over again, that you have to refine your data set creation alongside the problem to try to target the thing that you want.
Maybe there should be some sort of adversarial. It's looking for examples that are.
Yeah, that's a good point. Yeah, I think that would be definitely a next step, especially as you try to refine this further. I mean, so domain expertise is one side of that, but there's probably a learning side as well. And so yeah, this gets at like a fundamental theme here that I've seen. I know there are elements, areas of math where data is scarce, lots of them, but in where we've been working, it has not been the case. You've been able to generate usually as much as you want. And so there's this interesting duality where in the machine learning I usually do, I really work hard to make sure the model and the training regime is all fitted to this little bit amount of data I have. Whereas here we can kind of modify both. So you can change the model to do better, then you can refine the data set to more fit the problem you want to answer. The other thing that comes up a lot, and actually has already been preceded by one of the discussions yesterday and the day before, is representation matters a lot. You know, I think coming into this, I thought, well, you know, the model, if the representations are equivalent, then the model can learn to translate between them. It's definitely not the case, or at least not for the models we've been using, and it doesn't make it any easier. So as a really simple example, one can try to predict the parity of permutation. And this is known to be hard with a lot of architecture, so transformers are notoriously bad at parity tasks, or really any task where one change to like a coordinate will cause a big change in the output. It makes sense. But of course, the representation you use of the permutation can have a big effect on this. And whereas in things like computer vision and language, this community has kind of settled on a representation that everyone kind of uses small. I mean, you can use different tokenizers or things like that, but overall, people aren't using radically different representations of natural language that I'm aware of. In math, different communities can use representations of things that look far different. So maybe in combinatorics, the combinatorialists I work with often use one-line notation for a permutation, which is one way of representing it. As an algebraist, I used cycle notation, which is another. They don't really look the same, even though they're equivalent. And so making sure to evaluate through the list of representations, at least initially, seems really, really important. What do you do when you don't really know what the solution is? Then you have to try a lot of things because you don't have an idea. So another point, so one of our other data sets housed on loose-stick polynomials. This so far is just predicting coefficients of a given degree. Again, there's a lot of these. I think the interesting thing in this case is that and one of the things I think it makes it hard for mathematicians is some of the phenomena one sees don't happen until you get to really large values of n, where in this case large is like 10. But there's a lot of polynomials there, and so it's one of these interesting cases where you can conjecture that some pattern holds. So for example, a specific coefficient called the mu coefficient is either 0 or 1 from n equals small n to n equals 9, and then at n equals 10 suddenly you get other values. And at that point there's hundreds of millions of polynomials, so you're at a very high scale before something different happens. So this seemed particularly interesting in a place where machine learning could be of great value for those scales at which it's hard to do things by hand. And indeed, the models don't seem to have any problem with operating at that. I mean, at some point you'll get to where you can't even show the models enough training data because there's so much. But we have not reached that point on any of our problems. And the models, in fact, more data seems to almost always be more helpful, even though the problems get in some sense harder. And so that's the final point I would make, is that from my perspective at least, this is going to be a really valuable tool and will be complementary to mathematicians, helping to expand our intuition beyond places that maybe previously, for me at least, I was able to go by being able to look for patterns in data sets that are much larger than you could do kind of by eye or by working through a few examples. So. And I don't think, like, we've heard some really sophisticated things. I think there's low-hanging fruit that can be obtained even from non-sophisticated means, so really simple models. That's probably not all or even most problems, it's probably a few, but having this as a tool that people can use, I think there are problems out there for which there's probably some low-hanging fruit. Oh yeah, and again, we've seen more data matters more. There's one example we found where more data did not help. So quivers have infinite mutation equivalence classes. Of course, how do you get more data there? You sample deeper and deeper. We found that actually, as you generated more data by sampling more deeply in that equivalence class via quiver mutation, the models did slightly worse. So there are a few examples where things are harder. So in general, these data sets are not hard in the sense of raw accuracy numbers. I think the more interesting thing is to try to see if we can interpret them and understand what they're doing. Are they doing the same things mathematicians are doing in the known cases? Can they help us find new insights in the cases that are unknown? And then finally, I'll just end by saying there's a big question that we always get at ML venues is like, what do LLMs do on this? We have not fine-tuned an LLM for these problems. That would be interesting. We have done a little bit of preliminary in-context learning, so feed the model a whole bunch of like hundreds of examples of the problems. And what we found is they're actually, at least for when the number of examples are limited, they are somewhat competitive with small narrow models that have been fully trained for this, which is very interesting. That begins to diverge as the models get, the data sets get bigger and you can have fewer, we have the computational power to do fewer in-context examples. But I think the book is still open on this and there's a lot of things you could ask. We did kind of the simplest and least compute intensive thing you could do. So I think I will end there. Thank you.
Yeah, it's interesting. It's definitely worth discussing, what this type of data set or website provides, because as you say, it's not really a benchmark in the sense that it's exactly just provide some measure of performance. But certainly you could regard it as a central way of exchanging information about these very well-known and classic and interesting problems. And I mean, one thought that comes to mind is that there are a lot of results in this field, which is, of course, in all these are, but let's talk about this field where it doesn't really rise to the level of publishing something. You know, you try this kind of good idea and it didn't really work, or it didn't work as well as, you know, whatever. There's some kind of, you know, it's still worth publicizing someplace because it's an obvious idea. You try and you learn something, you know, but it doesn't rise to the level of writing a paper.
Yeah, I think that's a great point, and I mean, we ourselves have examples of this where we've seen some interesting observations. Weren't really able to prove a big theorem around them, but it seems like something that should be stored somewhere
Yeah,
for
and yes,
the
maybe
future.
this website is the place to do that.
Yeah,
It's
yeah.
sort of like, it's a loose analogy, but you know, like mathematical reviews, you know, when people write a review, it's not like it's a, you know, a separate publishable work, but it's still a contribution and benefits the community.
Yeah, and maybe by being collected somewhere, there's some sort of value that accumulates. If you can see a lot of this,
Yeah,
these small
yeah,
things,
yeah,
then
yeah,
you can
yeah,
say
yeah.
something
Maybe
bigger.
that's,
Yeah.
Changing results about these problems.
Yeah, okay, I like that a lot. We'll definitely keep that.
This website is not yet available.
It is, but it's a little, it's in the we're in the process of reworking some things, so you're welcome to visit it, but
So on this website, we can get the data sets and
Yeah,
also
yeah.
the models, the standard.
we will be putting up weights for models. We haven't done that yet.
So this is the benchmark.
Yeah, we initially used the word benchmark and then we got some feedback, some valuable feedback from numerous reviewers that like wasn't exactly a benchmark. If people are getting 99% on some of the data sets.
And as you say, the goal is different from the.
Exactly, yeah. Yeah.
I probably don't understand why is this not a benchmark?
Well, like it says, the point is not to to raise the number. Most machine learning tests, there is some intrinsic value to the number.
That's true. I guess it correlates with the goal.
I mean, maybe it's like a benchmark for interpretability or something, I don't know. But yeah, I mean, the one of the reviewers said, quite rightly, like you're saying this is the benchmark, but some of these data sets you get 99.9, like there's not much room for improvement. What do we
And
need?
almost all your data sets, there's something, some choice in terms of, you know, how, you know, what's the maximum, whatever it is, you know.
Yeah.
And size of example.
Sure.
How do you choose that?
We found that the sweet spot seemed to be, for a lot of these problems, the sweet spot seemed to be hundreds of thousands of examples. Tens of thousands was, you still saw the performance going up. Millions was fine, but like you started to saturate around
Do
hundreds.
you actually, do you provide an actual data set, or do you just, here's the algorithms?
So we have data sets for some values of n, but we also, for the data sets we created, in most cases, the code is uploaded, in a few cases it still needs to be uploaded so that people who care.
I mean, but I would say it's just as important to have the codes or.
Yeah.
You know, again, there are most, I would say, most math problems, there's some kind of an edit or something.
Yeah.
That you want to systematize that.
Yeah, I mean, I was curious whether, because as n goes up, the problems get harder in some sense. I mean, it's harder to deal with permutations of 20 elements than it is to deal with permutations of 3 elements. But also you get more data available, and it seems like usually in most cases, the more data outcompetes the fact that the gadgets you're working with are somewhat more.
Yeah, there's that, and that, you know, math, it's like data, there's kind of in between things. You know, as 50, there's no way you can have the data set, I mean, just so, you know, negligible sample of it, but you know, maybe your learning program, maybe your model knows something about symmetric groups, so yeah, it doesn't have to go through, you know, data the same one.
Yeah,
Since the data set's multiple.
yeah, exactly.
All sorts of possibilities. So, I mean, other, you know, just kind of, maybe you already have, you know, a few kind of standard references to get into the product, you know, it's like the current list of open conjectures and something.
Yeah, so so far we've tried to provide some context. Those have admittedly been kind of written, they need to be rewritten, and I think ultimately it'd be nice to have several open. A lot of these problems have data sets, you could associate several, a number of open problems with them. So having those would probably, having a longer list is on the to-do list essentially.
Yeah, I mean, I think, if you look at models, I mentioned that. Spectral function, all these things are totally obsolete now, but in this domain, it's not obsolete.
Yeah.